I'm Colleen Rosales. I'm the Strategic Partnerships Director at OpenAQ. We're a nonprofit aimed to fight air inequality through open data. I'm also a postdoctoral researcher at the Air Quality Research Center at UC Davis. And today I'm going to talk about correlative analysis using the Wolfram language for instrumentation used in atmospheric chemistry.
All right, good afternoon, everyone. Welcome to the last talk of the day before the Innovator Awards and the keynote dinner. My name is Colleen Rosales. I'm the Strategic Partnerships Director at OpenAQ. We are a nonprofit aiming to fight air inequality through open data. I'm also a postdoctoral researcher at the Air Quality Research Center at the University of California in Davis. And today I'm going to talk to you about the high throughput correlative analysis that I've done using the Wolfram language for instrumentation used in atmospheric chemistry. So a little bit about what I'm going to talk about today, a little bit of scientific introduction about air pollution, what we use, the type of instrumentation that we use to measure different pollutants in the atmosphere, and what I've done using the Wolfram language in terms of data organization, data visualization, and some statistical analysis with the data that we've collected. So air pollution, we're all familiar with the air we breathe. Air pollution is the second leading cause of premature mortality. 1 in 8 deaths are caused by air pollution. What we see here is a diagram of the human hair and the comparison of how small some pollutants are. So what is shown here is particulate matter with a diameter of 2.5 microns and 10 microns. So we call those PM2.5 and PM10. And mostly the instrumentation that's being used is based on how small these particulate matter are. And they're of concern because as they get deeper into the lungs, they cause more respiratory issues, cardiovascular issues. And nowadays, there's been a lot of instrumentation that has been developed to be able to measure these types of air pollutants. Some of them are more real time that can measure in every second or every minute. Some of them are more traditional and measure these using filter-based methods. So I've mentioned, the sampling that's more high frequency, sometimes per minute or per second. So nowadays, we have what we call low-cost air sensors as well as reference grade monitors, which can measure these air pollutants in real time. And OpenAQ, as I mentioned, we're a nonprofit that's aimed to fight air inequality. And what we do is we aggregate all this publicly available air quality data in real time. And so when you log into, or when you go to openaq.org and search for a certain location, you'll be able to see the real-time air quality in that location. So sometimes, there is, okay. So there's these methods that do more frequent analysis or more frequent collection of air quality information. However, the EPA still considers filter collection as the gold standard. And what do we mean by filter collection? So you have a filter and then you suck air through it, and then that collects that air for 24 hours, and then that sample or that filter gets replaced every 3 days, and then the filters get sent out to chemical laboratories that then analyze the air pollutants within that filter. And so the dust that has been collected in that filter can contain a lot of many different pollutants or many different compositions, such as elements, ions, organic carbon, and whatnot. And so basically the filter can tell a story on what the source of the pollution was. So for this specific analysis, I'm going to focus on the elemental composition of the filters that have been sampled. So this is work that I've done with the Air Quality Research Center in UC Davis. So the good news is that in the recent years, the pollutant concentrations have gone down. So that's good in terms of air pollution, but that has challenged our instrumentation methods. So our current analysis technique for elemental composition is called EDXRF, or energy dispersive X-ray fluorescence spectroscopy. And this technique can measure a lot of elements in the periodic table, as I show here, in purple and pink. But as I mentioned, because the pollutant concentrations have gone down through the years, this has challenged our current method. And now the elemental concentrations that we measure are at or below the detection limit, such that they're coming out as noise currently. And so now the question for us is, what other technique can we use instead of XRF? And this is where the other technique, which I'm gonna refer to as ICP-MS, comes in. And we wanna know, are these two techniques equivalent, or is ICP-MS better than XRF? Or is it possible that we can mix and match these two techniques to look at different elements in the periodic table? So the question for us is, how well can one instrument reproduce measurements from the other, and what instrument can we use if we're looking at certain elements in the periodic table? All right. So first of all, as I mentioned, we have these filters. We send them out to different labs. So one lab is the UC Davis AQRC. They measure using method 1, which is XRF. And then the other lab that we sent out the filters to is RTI International, and they do another kind of elemental analysis, which is ICP-MS. And these two labs, because they're different labs, they have different methods of analysis, they have different data outputs, basically. So one lab will have a SQL database for all the XRF measurements, and another lab will have an Excel file that they will send us. And it has the concentrations for all elements, for all filters. But then the question for me is, how do I match up all these filters and make sure that the element corresponds to the filter that I was looking at? And so that's the first step, is the data organization. And then the next step is for me to visualize and look at trends, and do the trends make sense? And also, it's kind of a sanity check for me too. If I see that the trend for this element seems to make sense, okay, our analysis is good. And then on a more quantitative analysis, we do also some statistical analysis. And then, an even more rigorous element by element instrument comparison to answer our question of, which element do we use, or sorry, which instrument do we use for specific elements? So first, in terms of data organization, so I used the Dataset functionality just because, it's both human readable and machine readable, or computable. And so it's easy for me, and it's also easy for Mathematica to operate upon. And so what I show here is the data set for one element for all 355 filters. And so I'm able to see clearly that, this column was analyzed using ICP-MS, and I am able to name each column according to what would make the most sense to me. And then now, I compute that data set. So for example, I want to look at, just want to make sure that all elements that are analyzed and I want to look at are, being reported in that data set. So that's what this shows us. And then next is, I want to make sure that, I'm able to extract the concentrations that were measured. And so this one represents, this name represents the concentrations that were measured using XRF. And note that I can either choose to do indexing, or I can choose to call it by the column name. And so that makes it, more accessible in that sense. And so that kind of reduces the error transformation in that step for me. All right. And then another information, piece of information that I don't want to lose is where was that filter sampled from and when was it sampled? And so I know the filter barcode, that's what is reported back to me by another lab and the corresponding concentrations for each element. But what they don't have in the Excel file is the site name, for example. And so I'd have to link that back to our current database and make sure that these are the samples that correspond to these barcodes. And so I also, again, use the dataset functionality to make sure that, the site names as I expect them to be are, being analyzed as well as, when they were sampled and whatnot. And that allows me to make sure, again, are these what I expect them to be? And the good thing with the dataset is it can be operated like a list. And so I can do some tally or reverse sort by. For example, I want to make sure that the sites that I intended to have more samples have more samples. So for example, the Boston samples, which I know are co-located, have the most samples, and that's the way I intended this analysis to be. And then there's just some sprinkling of the other sites. So, a lot of sanity checks along the way. So that's the data organization part. The next part is for me to visualize all of these data, look at the trends. Do they make sense? For example, if I know that one location is an urban location, then there are trends that I expect to arise. For example, elements that are usually seen to come from vehicular sources. For example, copper, zinc, barium, iron, titanium from brake wear, or zinc and iron from tire wear. So I know that these elements are correlated from these sources. So from the literature, this has been determined by previous researchers. And so I want to look at my data set. Do these correlations exist? And if so, good. So what I show here, so I did this correlation analysis using three different tools. So the first is a native system function using matrix plot and correlation. What we show here. Oops. So we have a heat map based on the Pearson correlation coefficient R. And so we map this grid of the different correlations of the elements. And so, for example, like I mentioned a while ago, if we know it's a roadside sample, we would think, or if it's a anthropogenic influence sample, we know that, for example, iron and titanium will be, highly correlated. And so this allows a quick view of which elements seem to make sense that they are correlated. So I think we check out there. So next is, if you want to look at the scatter plots themselves, so this is something that is not native to the Wolfram language, but thankfully we have the Wolfram function repository where we can look at the pairwise scatter plot. And so what we look at here, oops, it's a little too big for the screen, but what we see here are scatter plots of the different pairs. So this gives us a little bit more information. And then you can see that, there's these correlations, they kind of lie on the one-to-one line. And for example, if you look again at iron and titanium, so over here, iron and titanium, all right. You see that correlation, and then with a little bit more information rather than just a heat map gradient color. But then what we lack here in this plot is that, one, there's no range or no frame ticks in this plot. And also, so this is actually a log scale plot, which you can't tell by just looking at this, unless I scroll up and you see the label up there. And so that's kind of lacking for my uses, as well as you will note that the information on the uh, bottom left is mirrored on the top right. And so to be able to kind of put more information, even more information in this matrix plot, I also did a more customized version of the matrix plot. So in this case, I have the same comparisons of the elements, but what I did is that I have a different set on the bottom and then a different set on the top right. So the bottom left are measurements that were made using method 2, which is ICP-MS. And then the top right are measurements that were done using XRF. And so here there's even a lot more information. And then I was able to put the frame text and then so now it's very clear, although it's kind of small, but it's very clear that these are log scale plots. And then just to be even clearer on what elements are being compared, I put the labels instead on the one-to-one line. So those are the three ways that I'm able to visualize all these inter-elemental comparisons. But the actual so the actual meat of the comparison, and going back to the question of which instrument do we use? Do we use XRF method 1? Or do we use ICP-MS method 2? Or do we use a combination of the two? So to be able to do that comparison, so I plotted XRF versus ICP-MS, and then just plopped a unity line in there, so which is the black dashed line, and we can see right away that some elements perform well on both. For example, potassium, all points lie on the one-to-one line. Same with iron. There's like a couple points here and there that don't lie on that line, but mostly all of them lie on the one-to-one line. And then there are some elements that seem to perform well on one instrument. For example, for example, zinc, that kind of performs well on the higher concentrations, but on the bottom, it's a lot more spread out. And then some don't really do well on that intercomparison. And then even more so on the health-related elements like lead or manganese, strontium, even chromium and nickel, they don't really perform really well on that intercomparison. But what you will notice here is that what I put on the x-axis and the y-axis are quite arbitrary. So we don't necessarily consider any one of these two as the correct method. It's kind of like when you have a clock, you know what time it is, but if you have two clocks, you don't know what time it is. So these two, we're not sure. Some of them may, be performing well for some elements, but some not really. So in this case, it's not really applicable to do ordinary least squares, which is a model 1 type of regression, which initially, this is kind of the dangerous thing that some people do in terms of correlations, is to blindly apply model 1 techniques. In which case, for the current situation that I have, both XRF and ICP have uncertainties related to these measurements. And so it's kind of arbitrary what I put on the X and Y. But what I wanted to have be shown there is that the regression should be able to take into account the uncertainties both in the X and Y axis. And so that's something that I'm working with Nick Brunk of the Wolfram Alpha Math team to have these model 2 techniques as WFR functions. So there's already the Thielsen line, which is already previously there, but there's also, we're working on standard or reduced major axis, as well as major axis regression and Bartlett 3-group method, all of which will be able to take into account the errors in the X and Y axis. And yeah, with that, I'd like to summarize the talk on how I was able to use the Wolfram language in kind of all aspects of that, starting from the data organization, starting from the moment that I got the data from the data sources, then how I was able to visualize that quickly with the matrix plots, and then also using the scatter plots, and then further into the more quantitative statistical analysis with the use of both system functions as well as WFR in the future. So these are some relevant talks, and I think most of them were done today. But yeah, I'd be happy to take any questions. Thanks. Not at the moment. I'm not sure actually if the pairwise scatter plot already has it in there. I haven't explored. Maybe it's already has it in there. I just looked at the visual of the pairwise scatter plot. So that's another aspect of it that I'm not intending to look at. So what I'm trying to do here at least is to be able to suggest a method to measure, but the prediction is a whole nother game because there's a lot of equations, chemical equations involved. The precursors for the pollutants, for example, you need the rate constants for them and whatnot. So that's a whole nother game there. Yeah. Especially for wildfires. So for here, the current method, which is XRF and ICP, they're not very good in measuring carbon, but there are methods that are specifically targeted to carbon, which also AQRC at UC Davis measures. They're called elemental carbon, total organic carbon. So all sorts of carbon analyses, which are not covered in the elemental analysis here. But yeah, people are doing that too.